We'll move on to the types of relative extremes we have. The first one is relative maxima or maxima, and then we have relative minima or minima. Okay, so say we have this graph here also, which also shows how we are going to deal with what is called the minima and then the maxima. Okay, so say for a range of products, maybe you are a producer producing, say, pens or phones for students or workers at a particular financial institution. Okay, at a point you'll be making the highest profit, right? At some point you'll be incurring losses, but that is the least possible cost, right? If it has to do with profit, you'll be getting the highest profit or the least possible cost. So let's take the maxima as profits, highest profit, minima, say minimum cost, right? Maxima, say maximum profit or maximum revenue, minima, say minimum cost, right? So we have the local maxima, minima, global maxima, and then the differential of a function where it doesn't exist, right? So maxima has to do with maximum point, minima has to do with minimum point. At this point, we would say that say we have a class of students, right, who are taking exams or for the sake of maybe their end of sem, right? We have, let's say, 3 classes. Okay, we combine those 3 classes together, and we have maybe 3 students, that's one from each class, topping the class. Let's say group 1, someone tops group 1, group 2 same, group 3 same, right? That is, they are called the local maxima. So locally in their group they top, right? But if we bring all those people who top in their various groups together to get the overall best students or the overall top scorer, then that person, or at that point, we will say it is a global maxima, right? And then we have the minima as well here. So, like I said, maxima has to do with maximum point, minima has to do with what? Minimum point. Because as a producer, or let's say as a manufacturer, we would want to achieve the highest profit or possibly incur the least costs, right? So the highest and lowest points are called points of relative extremum. The curve is locally maximum or minimum. Under this relative maxima and minima, we have conditions under them, and that is what we have here. The first one is called the necessary condition for relative extrema. The idea about this rule or this condition is that when you have a function, or you are given any function, or you find that function, differentiate the function, equate it to 0 to get the values of x or the value that you want, right? So at local minima or maxima, it is called a relative extreme. Differential is equal to 0. However, cannot tell exactly whether the point x, where f of x, right, f prime of x is equal to 0, is indeed a maximum or minimum. We need another rule to help us. So say we've been given a range of production. Say we are producing pens for a particular primary school, and the range of product is to produce 0, that is nothing, or produce 130 pence for them, right? If we have a given function like that and we differentiate the function, equate it to 0, and then we get quantity to be produced for the school as, say, 30 or 20, right? It means that if we produce just 30 units out of that range of product 0 to 130, that 30 will give us the highest revenue. Let's say we're talking about revenue here, or to give us the maximum revenue, right? But you are given a range of production. You can produce 0 to 130. Well, you can't just consider the 30 to be the one to give you the highest revenue, right? So we need another test to confirm or to show that indeed, if you produce just the 30 units out of the range 0 to 130, that you can consider 100, 120, and the rest. This second test will tell us that indeed that point 30 will give us the maximum revenue or the maximum profit, right? That is called the sufficient condition, right? This is also saying that take the second derivative of what you differentiated. So here you do the first differential, and what you get, differentiate it again here. That's what this is saying. If you take the second derivative and it's less than 0, then the point is a relative maximum point at that value or the other variable, say a or x. But if you take the second derivative of what you differentiated and it's greater than 0, then the point is what? A relative minimum, or it is a relative minimum point, or a minimum point there, where the second derivative at y of y at a, right? So basically this is the idea, general idea, but take the second derivative of what you have. If it's less than 0, it is a maximum point. If it's greater than 0, it is a minimum point, right? On our next slide here, we have a practical example to show how you go about a minimum and maximum point. So given the function y is equal to 2x squared minus x4, find a point at which either minimum or maximum occurs, right? Indicate whether a relative extreme from the question is whether a relative extreme from question is a relative maximum or minimum point, right? So what do you do? We have the function already. Differentiate that function, right? This is what we have here after differentiating it. Find the values of x, right? So we are saying that this is the point where the relative maxima and minima occurs, right? So what do? We do the second test, right? To establish f of x attains a minimum or maximum values, we apply the third rule, that's the sufficient condition. Take the second derivative of this 4x minus 4x to the power third, and the differential of that will give you this, right? Okay, now what do? The next thing is that put this value 0, 1, negative 1 in place of x over here. First, at x is equal to 0, we had it to be 4, which is greater than what? 0. If it's greater than 0, it is a minimum point. Here we have 1, into it we had a final answer of negative 1, which is less than 0. At that point, the function is a maximum point, sorry. At x is equal to negative 1, after substituting it, we had negative 8, which is also less than 0, and it shows that that point is indeed a maximum point, right? I hope we get this general idea about relative extrema. Let's look at this illustration or this example that will help us to apply this in the business sense, right? So suppose the price is given as P is equal to 80 over Q. 80 minus Q all over 4 for the range 0 to 80, where Q is the number of units of product. At what value of Q will maximum revenue be attained? Maximum revenue. What is the maximum revenue, right? This is an application of the relative extrema. So we're talking about maximum revenue or total revenue. How do you get total revenue? It is price times quantity. We have the price function here to be 80 minus Q all over 4. We just multiply that by Q, and then we have 80Q minus Q squared all over 4, right? At the quantity where maximum revenue is attained, the differential of the total revenue function, that's what this is saying, is equal to 0. So what do? Differentiate this function, equate it to 0 to get the quantity, right? So on our next slide here, the differential gives us what? 80 minus 2Q. If it's equated to 0, our quantity will give us 40. What does this mean? It means that looking at this range from 0 to 80, if we produce just 40 units of the product, we are going to achieve that maximum revenue or that highest revenue. So given the nature of the revenue function, then at quantity being equal to 40, revenue could be minimum or maximum. To establish whether it is a maximum or minimum point at Q, which is equal to 40, we use the second derivative test, i.e. the sufficient condition. Take the second derivative of the differential. The differential here is what? 80 minus 2Q. If we differentiate this again, second derivative, it gives us minus 2, which is less than 0. What is it telling us? It means that that point is indeed a maximum point. It also means that, right, if you produce just 40 out of the range of products 0 to 80, we will get the highest revenue. Thus, Q is equal to 40 at a quantity level which generates the maximum revenue possible, right? Revenue is equal to what the total revenue function is 80Q minus 40 all over what? 4. 80Q minus Q squared all over 4. That's the revenue function. To get the maximum revenue, we just substitute the 40 in place of Q. We have a maximum revenue of 400. In this sense, it means that if we produce 40 units or 40 products, right, we are going to achieve or attain a highest or the maximum revenue of $400 or 400 Ghana cedis. In the sense, this is one of the reasons why we have to learn differentiation, right? So as you can solve problems like this in the business sense. So this is how you apply it in the business perspective.